Hello, this is Mr. Mac. We're talking this session about factoring polynomials and using the concept of factoring polynomials to solve polynomial equations. Our focus is going to be mostly on quadratic polynomials. Okay, now many quadratic polynomials can be expressed as the product of factors. Now, an example might be something like x plus 5 times x plus 3. This is a product of two binomial factors, and when you FOIL these out, and FOIL is something that every algebra student probably knows, you get x squared plus 8x plus 15. Now notice the 8 is the sum of the last term in the first binomial and the last term in the second binomial. And the product of 5 and 3 is the 15, the last term in the quadratic polynomial. So what we're going to be doing many times is looking to see how this FOIL process would have happened when we are given something like this. Okay. Now, why is it important to be able to identify the factors of a polynomial? Well, there's a very, very important concept called the zero product property. Now, I want you to think about this with me for a couple of minutes. Let's say I were to tell you that A times B was equal to 0. And A and B were real numbers. Now, I'm going to make a statement, and I want you to think about it and see if you can verify it in your mind. I'm going to say, it is impossible for this product to be equal to 0 without one of those numbers being 0. There are no two non-zero real numbers that can be multiplied together to get 0. Well, think about it for a minute. Pause the video perhaps. See if you can come up with two numbers that both aren't 0 that multiply together to be 0. You back? You couldn't find one, could you? So the zero product property says if the product of two numbers is 0, then let's do it this way. If A times B equals 0, then A equals 0 or B equals 0 or both equal 0. But anyway, so if the product is 0, then one of the numbers at least has to be 0. Now, what that means is if we have a polynomial like x squared plus 8x plus 15, and we know that it's equal to 0, if we could find two binomials that multiply together to give that polynomial, and we know that their product is 0, then one of those binomials has to be 0. Well, now, notice this is the same polynomial that we had up there, so we know that the factors of this polynomial are x plus 5 and x plus 3. So if x plus 5 times x plus 3 equals 0, by the zero product property, x plus 5 has to be equal to 0, or x plus 3 has to be equal to 0. And if that's the case, then we can solve this first equation easily. We get x equals negative 5 when we subtract 5 from both sides. And the second one becomes x equals negative 3 when we subtract 3 from both sides. Now, what we ordinarily do then is we would identify the solution set to be x is an element of. This means x is one of the numbers inside this set. And the numbers inside this set this time are negative 3 and negative 5. Now let's just go back for just a second and let's check this. If we have negative 3 squared plus 8 times negative 3 plus 15, when we square negative 3 we get 9. When we multiply 8 times negative 3 we get negative 24. and then when we add 15 is 15. So 9 minus 24, or plus negative 24 is negative 15, and negative 15 plus 15 is 0. So negative 3 actually makes the equation true. And let's try negative 5. Negative 5 squared plus 8 times negative 5 plus 15. Well, negative 5 squared is 25. 8 times negative 5 is negative 40 plus 15. Now, when we add 25 and negative 40 together, we get negative 15, and negative 15 plus 15 is 0, so that one checks as well. So notice we got two numbers that actually make this equation true. It's kind of what we're expecting. Anytime we have an equation that has degree 2, in other words, the highest exponent on the x is 2, we're expecting two answers. Sometimes those two answers will be the same. And actually in the last section, we looked at the fact that sometimes the quadratic polynomial, which represents a parabola, doesn't cross the x-axis. But basically, we'll get back to that, and we'll decide that the answers, there need to be two answers, but maybe our set of numbers isn't large enough yet. Okay, now, what that means, though, is if we have a polynomial equation, if we can move everything to one side, get it set equal to 0, and then if we can factor the non-zero side of it, we can set each of the factors equal to 0, and we can solve the equation. So now the question comes up, how do we factor polynomials? Well, we're basically focusing on quadratic polynomials and when second degree polynomials, and we'll come back and we'll add to this list a little bit. But I'd like to start a checklist of things that you should do when you're trying to factor. Okay, and we'll call this a factor checklist. Now, the first thing you should always check for when you're trying to factor a polynomial is common factors. Common factors can greatly complicate a polynomial, and if you take them out first, a lot of times you'll be doing yourself a big favor. Let's take a look at an example. Let's say you have x squared minus 9x equals 0. Okay, we've got a polynomial on one side, we've got it set equal to 0. We want to solve this. So one of the ways to solve this is to factor that polynomial. So the first thing we ask ourselves, are there any common factors? And in this case, the answer is yes. X is a common factor, so we're going to take that out. X times what? Well, x times x gives us x squared, and x times negative 9 gives us 9x. So now we have two factors, x and x times minus 9. So x equals 0, or x minus 9 equals 0, in which case x equals 9. So x is an element of the set 0, 9 in this particular case. Notice the common factors. The common factor enabled us to solve this particular equation. So, guys, always, 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 just pause for a second, look at the thing and say, are there any common factors? If there are, take them out. Okay, and that will simplify your equation. It'll make things a lot nicer. Now, the second thing you should check for is a thing that is usually called special products. Now, it turns out that there are two special products that we really want to focus on in this particular section. The first special product is what happens when we have a binomial with the sum of two numbers, and then that's multiplied by a binomial with the same two numbers but the difference of them. In other words, a plus b times a minus b. Now, when you FOIL a plus b times a minus b, you get a squared, that's first. Outer, you get negative ab. Inner, you get positive ab. And last, you get negative b squared. Well, now these two terms are the same, except they have opposite signs. When you add them together, you get 0 of them, or they go away. So you get a squared minus b squared. Now notice, a squared is a square. There's something you square to get a squared. Actually, it's a. And b squared is a square. There's something you square to get b squared. Actually, it's b. So we call this pattern the difference, because we're subtracting, of two squares. Now, this is a pattern for us. Anytime you have the difference of two squares, it factors into the two numbers added together and the two numbers subtracted from each other that are the numbers that you squared to get the first term and the last term. Example, x squared minus 36. See, now, this is a binomial that is the difference of two squares. You square x to get x squared. You square 6 to get 36. So this factors into x plus 6 times x minus 6. And they can get more complicated than that, but it works out the same. If you have that pattern, you should recognize the difference of two squares. Now, the second pattern that we want to deal with is when we have a binomial itself being squared. And let's see what happened there. There we go. See, if we have something like a plus b, and it is being squared, there's a mistake here that Algebra 2 students love to make, and you have to watch out that you don't make it, because it's a horrendous mistake, and when you make that mistake, everything else you do in the problem will not be correct. See, a plus b squared is actually telling you to use a plus b as a factor twice. In other words, a plus b times a plus b. Now, if you FOIL that out, you get a squared, that's the first, ab for the outer, ab for the inner, and b squared for the last. Now, ab plus ab becomes 2ab. Now, this is the pattern, and any student who has this and gives me this without this term has actually distributed the exponent through the plus sign, and you've gotten a wrong answer. You will always get the wrong answer when you do that. You have to write the binomial out and square it. But now, the good news is that this is really the pattern of what you get. Now, if you look at this, a squared plus 2ab plus b squared, you can think of a as the first term in the binomial, and you can think of b as the second term in the binomial. So if you want to square a binomial, you get the first term squared plus 2 times the first term times the second term plus the second term squared. So if you had 2x plus 5 squared, you could, if you wanted to remember this pattern, and you really should, do this. The first term squared. Now, in your head, you square 2x. 2x times 2x is 4x squared. And then plus the 2 times the first term times the second term. 2 times 2x is 4x. And then 4x times 5 is 20x. And then plus the second term squared, and that's 25. So notice we've actually come up with the answer to the square of this binomial without actually having to FOIL them out, and that's pretty powerful. But the reason this is important here is because if you have something like this, we're kind of going to expect you to recognize it and realize that that fits the pattern of the square of a binomial, and recognize then that it would be 2x plus 5 quantity squared. It's another one of your special products. It's not really a biggie on this one. If you don't recognize it, you can get it for under number 3, but still, you'll save yourself a lot of time if you do recognize it and get it here. So learn this pattern. The square of a binomial is the first term squared plus 2 times the first term times the second term plus the second term squared. Now there's just one additional thing I would like to mention here. If there's a minus sign here, then there would be a minus sign here and here, and here, and here, and there would end up being one here. So if you have a minus b squared, you get the very same pattern, but it's going to be minus 2ab in the middle. So whatever sign you have on this second term, that's the sign that's going to go inside here. All right, now that takes care of special products. The next thing that we need to do is we need to factor general quadratic trinomials. If it's not one of the perfect squares, but it's a general quadratic trinomial, then we would like to factor it. And this splits into two cases. There are cases that are simple, and there are cases that are more complex. Let's take a look at what I mean by the simple cases. Imagine, if you will, you have x squared plus 10x plus, let's go with plus 24. Now, if we want to factor this polynomial, we would go through the checklist. We would find there are no common factors. It isn't a special product. So is it a general quadratic trinomial? It is. It's got 3 terms, and it's a quadratic. So, and now, the thing that makes it simple is that the coefficient of the x squared is 1. When the coefficient of the x squared is 1, what you can do is you can simply put down 2 sets of parentheses to hold 2 binomials. Now, we know, or what we're saying is that these 2 binomials FOIL together to give x squared plus 10x plus 24. That means that these 2 numbers FOILed to give us x squared. It's pretty obvious they have to be x and x. Now, we know that these 2 numbers multiplied together to give 24, and when we did the outer and the inner, we added those same 2 numbers together to get 10. So the question you ask yourself now is, what 2 numbers multiply to give 24 and add to give 10? And the answer is 4 and 6. And that is a quadratic trinomial that's factored that's fairly simple. Now, I chose to do the first example with all plus signs, but there is no guarantee that there will be all plus signs, so you do have to watch out for the negative signs. Let's see if I can illustrate this. Imagine, if you will, that we have x squared plus 7x minus 18, and we want to factor this one. Now, once again, there are no common factors. It's not a special product. And it is a simple quadratic polynomial, so we put down the parentheses and we put x here and here. Now, the question we now ask ourselves is, what 2 numbers multiply to give negative 18 and add to give positive 7? And you must include the signs in that question. What 2 numbers multiply to give negative 18 and add to give positive 7? Well, 18 is 3 times 6, 2 times 9. 2 and 9 seem like they would work, because if you subtract 2 from 9, you get 7. But what we want is 2 numbers that multiply to give negative 18 and add to give positive 7. Now, if you think about it in a minute, that means it's positive 9 and negative 2, because positive 9 plus negative 2 gives us 7, and positive 9 times negative 2 equals negative 18. So watch what we do. Positive 9, are you watching? And negative 2. That takes care of where the signs go as well in factoring that quadratic polynomial. Now, you will get some practice on those general quadratic trinomials, so these 2 examples probably should be enough for that. But now, the second type of quadratic trinomial that you're going to be asked to factor is more complicated. I'll call them complex. Now, complex quadratic trinomials are quadratic trinomials that have a coefficient in front of the x squared. You can't ask yourself those same questions if there's a number in front of the x squared. Let's try an easy one here. Let's do 10x squared, and let's do 14 here. And what have we got? We got 4 plus 3. Well, let's use 39x in the middle. So 10x squared plus 39x plus 14. I think this is going to work. I hope it's going to work, or I'll have to go back and do this part of the video over. Now, here's the thing, and I must share this with you. Years ago, when I was in college, I was in a course called College Algebra and Trigonometry at St. Petersburg Junior College. And that course was taught by a Mr. Joseph Dorset. Now, Julie, I hope you don't mind this, but I'm just going to tell him. Mr. Joseph Dorset is Julia Withrow's grandfather. And he showed me a way to factor these complex quadratic trinomials that he actually had developed and put in a book, written in a book, and it was his. Now, a lot of other books after that took that method, and they call it things like splitting the middle term or the master product method, but he developed it. And so we're going to call it the Dorset method. Now, the Dorset method basically says if you have no common factors, no special products, then the next thing you're going to do is you're going to multiply the leading coefficient, that's the 10, by the constant to get what we're going to refer to as the master product. Now, in this case, the master product is 140. Now, what we're looking for is a pair of factors of the master product that add to give the middle coefficient. Now, a lot of times it's not really easy to see that at first, but you can write down the pairs of factors of 140, and even though this looks a little daunting, it turns out it's not too bad. And so let's just be orderly about this. 1 times 140, 2 times 70, 3 doesn't work because 3 doesn't go into 140 evenly, 4 times 35, and the fact is, that's the pair that works. So even though there are more, we can stop. We found the pair we're looking for. Now, once you have found the pair of factors of the master product that add to give the middle term, what you do is you split the middle term into 2 terms using these numbers. In other words, this polynomial becomes 10x squared plus 4x plus 35x plus 14. Now notice that 4x plus 35x is 39x. But what we've done is we've written it as 2 terms. Now, the next step in the Dorset method is to make sure that there is a plus sign in between the first 2 and the last 2 terms. If there's a minus sign there, you have to make that plus a negative before you go any farther. There must be a plus sign there. Once you have a plus sign there, put parentheses around the first 2 terms and around the last 2 terms, leaving the plus sign between them. Now, this does not mean we factored it because that's an addition sign, not multiplication. But we'll go on from here and notice wonderful things are going to happen pretty quickly. We look at this first pair of terms and we ask ourselves, what's the greatest common factor in this? And we find 2x. Now, 2x times 5x plus 2 is how that first one factors. Now, we look at the second binomial, and what's the greatest common factor in those? It looks like it's 7, and we're left with 5x plus 2. Now, if you've done this right, and you find these 2 numbers here, this will always happen. You'll get the same binomial in both of them. Well, one proviso here. If there is a negative sign right inside these parentheses, the factor you have to pull out here is negative for that to happen. Otherwise, this will be the opposite of that. So if you have a negative sign right inside the second set of parentheses, then pull out a negative factor and then it will happen. So now, by common factors, we can take out a 5x plus 2 and we're left with 2x plus 7. And so notice 5x plus 2 times 2x plus 7 gives us 10x squared plus 39x plus 14. Now, if you look at this, I mean, this is really a very simple and wonderful thing. If you look at this and you start with this step right here, if you were foiling, you would distribute the 5x plus 2 over this binomial. In other words, you'd have 5x plus 2 times 2x plus 5x plus 2 times 7. And then you would distribute the 2x to get 10x squared plus 4x, and you distribute the 7 to get 35x plus 14. And then the last step would be to add the 4x and the 35x to get 39x. What this method enables you to do with the master product is to identify how to split up this middle term into two terms so that you can, in essence, unfoil the problem. The 39x is the piece of the quadratic trinomial where information is hidden, and this master product will enable you to find that information so you can split the middle term and factor that polynomial. Now, I recommend you go back over this and try to do that, but what I'd like to do is I would like to do another example so that you'll see how this works also with negative signs. So I'm going to erase this now, not the whole thing, but this part right here, and we're going to work on another one that has some negative signs in it. So let's use 6x squared minus 9 minus 25x. I think that'll work. Let's see. It should work, yes. Okay, so let's use this one. Now, you ask yourself, are there any common factors? Well, 6x squared and 9 have common factors, but 3, and that's not in 25, so no. Is it a special product? No. So, is it a general trinomial? Yes, it is. And since there's a 6 in front of the x squared, it is complex still. So, we're going to execute the Dorset method. Now, the Dorset method is to find the master product, which in this case is, pause if you need more time, negative 54. Now, we're looking for a pair of factors of negative 54 that add to give negative 25. So let's write negative 1 times 54, negative 2 times 27. Well, you know, if we look at that as if it was 2 times negative 27, that would work, right? So that's what we'll use. Now, if you were listing them, you'd have come to it eventually, but I mean, I hope you recognized at that point that negative 2 and negative 27 were the ones. So now we're going to rewrite this middle term using 2 and negative 27. So 6x squared plus 2x minus 27x minus 9. Now, in this case, we can't put the parentheses in because there's a minus sign in front of the 27x. So I'm going to make this plus a negative 27x, and then I'm going to put parentheses here and here. Now, in 6x squared plus 2x, the greatest common factor is 2x. We're left with 3x plus 1. Now, since there is a negative sign right inside this parentheses, we need to take out a negative common factor, and that negative common factor is negative 9. Now, be careful on this. Negative 9 times what gives you negative 27x? Positive 3x. And negative 9 times what gives you negative 9? Positive 1. Look what happened. When you find these two numbers, that's almost guaranteed. So we have 3x plus 1 times 2x minus 9. That is general quadratic trinomials. Some simple, some complex. When they get to be complex, use the Dorset method. And I'll bet you Julia will tell Mr. Dorset to watch this particular part of the video. So hi, Mr. Dorset, and thanks so much. All right, now, the next thing in factoring quadratic trinomials, the fourth one in your factor checklist, is a thing that I call grouping, or that is called grouping. It's not my name for it. Now, if you have gotten to this particular point and you have not been able to factor any other way, then what you're left with is grouping. See if you can group things and factor terms out of some or something like this, and then somehow figure out how to factor more of it. Let's take a couple of examples of grouping, but grouping just requires some actual time spent with it. So let's take a look. AB plus AC plus DB plus DC. And if you were told to factor this, you look at this, common factors? No. Special products? No. General quadratic trinomial? No. Okay, so boom, we're down in grouping. Well, let's try grouping this. What we'll do is we'll group the first two terms and the last two terms. Now, are there any common factors in the first two terms? Yes, A. And we're left with B plus C. Are there any common factors in the last two terms? D. And inside we're left with B plus C. Now look what we have here. Now there's no guarantee this will happen on these, but if it does, we'll recognize it. B plus C is a common factor to both terms, and we're left with A plus D. So A plus D times B plus C is the factored form of that original polynomial. Cool? Now, it's not always true that you group 2 and 2. Let me show you an example of one that's grouped, say 1 and 3. How about something like x squared plus 4x plus 4 minus y squared? Are there common factors? No. Is it a special product? Well, no. Is it a general quadratic trinomial? No, there's 4 terms, so we go to grouping. Now, if you group 2 and 2, this is not going to help you. But watch this. If you group 3 and 1, this first trinomial actually factors into x plus 2 squared. And now, if you go back, notice you've got a square minus another square. That's the difference of squares. That's one of those special products. So you would write x plus 2 plus y times x plus 2 minus y. And that's just scratching the surface of grouping. There's a lot of other things you can do with grouping, but that's kind of the things that you're going to be looking for there. Now, there's one more thing that needs to be discussed before we end this concept video, and that's the concept of if you have the solutions you want to a quadratic equation, how do you get the quadratic equation that has those solutions? Let's say we want solutions 2 and 8. Okay, so we want x to be, we want a quadratic equation that has 2 and 8 as solutions. Well, now here's the concept we go through. Remember, solving quadratic equations by factoring was we split the polynomial up into factors, and then we set each factor equal to 0. So if we have the answers, we can write a binomial that has that first number as its 0. In other words, if you put 2 in for x in x minus 2, you would get 0. And we can write a binomial that has 8 as its 0. If you put 8 in for x in x minus 8, you would get 0. Now, if you multiply these together and set them equal to 0, that is a second-degree equation, quadratic equation, that has the 2 roots that you requested. Now, usually they want it in standard form, so we're going to have to FOIL stuff out here. But just think about this again now. If x is 2, this is 0, and who cares what this is? 0 times anything is 0. If x is 8, this is 0, and who cares what this is? 0 times anything is 0. So 2 and 8 make this equation true. Now, we can make it look more like a quadratic equation by FOILing these out. We get x squared minus 10x plus 16 equals 0. So there is a quadratic equation in standard form that has the solutions we requested. And that takes care of the concepts we wanted to discuss here.